Geometry, Chapter 8, and we're going to be looking at right triangles specifically, and we're going to be looking at some of the relationships in the right triangles, and we're also going to introduce you to trigonometry, which again are some relationships within right triangles that are very powerful relationships that are very useful in the world around us and in mathematics. In the first lesson here, we'll look at the Pythagorean theorem. I think most of you have probably heard of or seen this before. We'll look at how we can use its converse, how we can apply it, and then how we can use the Pythagorean theorem and right triangles for indirect measurement. You remember we looked at indirect measurement already with angles of incidence and angles of reflection. We also looked at indirect measurements using shadows. Well, using right triangles and trigonometry is another way that we can indirectly measure things, again, things that are difficult to measure, using proportions or using some things, ratios in geometric figures by superimposing them on the things around us. So the Pythagorean theorem was not invented really by Pythagoras. He's a Greek mathematician from the 6th century BC, and ancient civilizations, the Babylonians, Egyptians, the Chinese, used the properties of these right triangles in their construction and in their art and those types of things before Pythagoras, but Pythagoras was the first mathematician to prove the Pythagorean theorem. And there's several different ways to prove the Pythagorean theorem, but he was the first one to do it, and so the name stuck. The name, or the Pythagorean theorem, is this: in a right triangle. So that's the conditional. Again, a theorem is a conditional statement, and again, we're going to look at the converse later, so we want to know what the hypothesis and conclusion is. The hypothesis is if you have a right triangle, in a right triangle, then the sum of the squares of the legs is equal to the square of the hypotenuse. So that's the English way to say a squared, which is one of the legs squared, plus b squared. So that's the sum of the legs squared, equals c squared, or the length of the hypotenuse squared. So a squared plus b squared is equal to c squared. Now, this is a rather simple theorem, but there is one part that always gets confused and always creates some mathematical errors, and that is we must remember that c, the value that goes in for c, must be the hypotenuse, and that's always going to be the longest of the three values. A and B are lengths of legs, c is the length of the hypotenuse, and the hypotenuse will always be the longest value, or the largest value. So if you're given three numbers, and you want to substitute them into the Pythagorean theorem, you must put the longest or the largest of the three numbers in for c, because that is the representative of the hypotenuse, and the hypotenuse must be the longest, or will be the longest, of the three legs. Okay, so a squared plus b squared is equal to c squared. Remember, the hypotenuse must be the letter c. A Pythagorean triple is a set of three non-zero whole numbers that satisfy this equation. In other words, a Pythagorean triple are any three whole numbers, or whole numbers meaning not fractions, and you can't use zero. Any three whole numbers that, if you were to substitute them into this equation, putting the longer or the largest of the three values in for c, then this would be a true statement. You could square the a, square the b, and that would equal the square of the third. Okay, some common Pythagorean triples are 7, 4, and 25, 8, 15, and 17, 5, 12, and 3, the most common one being 3, 4, and 5. So 3 squared plus 4 squared is equal to 5 squared. So this would be a Pythagorean triple. Now, it's not really important necessarily that you know those or memorize those, but if you do begin to recognize those numbers when you come to a problem, you can save yourself a little bit of arithmetic time by recognizing that those are going to be a right triangle. They are going to make the Pythagorean theorem true. Now, the interesting thing about those triples is once you know what those triples are, then any multiples of those three values is also a triple. Meaning, if I take the numbers 3, 4, and 5 and I multiply them all by 2, then 6, 8, 10 is also going to be a Pythagorean triple. Or if I took 3, 4, 5, multiplied all the values by 3, that would be a triple. If I multiplied all the value by 4, that would be a triple. If I multiplied them all by 10, those would be a triple. So any multiple of a triple will also be a triple. And again, knowing those, memorizing those isn't really of most importance. It's just a shortcut that if you recognize them can save you a little bit of time with the arithmetic. So if we're given a right triangle and we're asked to determine the length of a side and we know it's a right triangle, Pythagorean theorem is always a possibility. And that's one thing I probably want you to remember. Not probably, you should remember because it would be very helpful. If you're ever trying to determine the length of the sides of a triangle, one of those little hooks you want to put in your mind is that if I'm ever trying to determine the length of a right triangle, Pythagorean theorem is always a possibility because all right triangles, this theorem is true. So here I have a right triangle. They want me to figure out x. Now the x value is the hypotenuse. I should identify that first so that when I substitute into a squared b plus b squared equals c squared, this x must go over here because it is the hypotenuse. So then I could put in a squared plus b squared is equal to c squared. And so c, solving for c, I take the square root, would be the square root of 8 squared plus 6 squared. So this would be the value. Now 8 squared is 64, 6 squared is 36, okay? So adding those together, that's 100, so the square root of 100 is 10. So the length of c would be a 10. Now, there's something important that I want you to notice here very quickly is you'll notice that I solved this here. Now, what you cannot do, and I want to show you what happens if you try to do it, is to take the square root of these separately. Whenever you have a plus sign or a minus sign between two numbers, you cannot do something multiplicative, multiplying, dividing, or square rooting or anything like that separately. In other words, you cannot take the square root of 8 squared and add it to the square root of 6 squared. These are not the same. If you took the square root of 8 squared, that would be 8. You took the square root of 6 squared, that would be 6. And if you add those together, you get 14. And you can see that 14 is not the same as 10. So even though you may write out your expression like this, and you will be doing this quite a bit because we'll want your answers in simplest radical form, resist the temptation to think that taking the square root before you square and add is going to give you the same value as if you squared them and added and then took the square root. So be careful of that mistake. Try not to make it. Another example or two. Again, because it's a right triangle, I want to find the length of a side in the right triangle. I can use the Pythagorean theorem. I just must be sure that my hypotenuse goes here. So I identify that this is my hypotenuse, so this must go in for the c value here. Okay, make sure you make that identification first. So a squared can be either one of these two, so I'll put in 16 squared, and then the b, or the second leg in this case, is x, so x squared is equal to 20 squared. Now again, I want to show you something. There's no reason to multiply 16 squared out here. Let's do all of the arithmetic and then we can do one calculation at the end, and I'll show you why. So 16 squared, whatever it is, needs to be subtracted over to the other side in order to get x by itself. So this is going to be 20 squared, whatever that is, minus 16 squared. And then solving for x, taking the square root of both sides, this is going to end up being 20 squared minus 16 squared. So what is x? Now if this comes out even, I can do this on my calculator in one step. Because my calculator has a square root function on it, I can do square root, and then I can just enter in 20 squared, because I have a squared key, minus 16 squared, and then I can do one calculation, and the answer is 12. Okay, I didn't figure out what 16 squared was, it doesn't matter. I didn't figure out what 20 squared was, it doesn't matter. I didn't figure out what those two numbers then subtracted was, because it didn't matter, and then taking the square root of that that is the only thing that matters. And because of technology and the way your calculator works, it's a lot easier just to enter it in like this one time at the end than to take the time to square it here, write that number down, and then square 20, write that number down, and then subtract them, and then write that number down, and then take the square root. All of that to get to the number 12, when you can do that all in one step on your calculator. So if you do all the algebraic properties down to the very end, you should only use your calculator once here at the very end in order to get your answer. Now, if you did that calculation and the answer did not come out even, like this one did, in other words, it came out to like 13.78 or whatever, in that case, then you're going to have to go back and do the calculation here by hand, find out this number, because in that case we want simplest radical form, which means whatever that number is, let's say square root of 158, then you'll need to do your upside down division, get your prime factors, so that you can write your final answer as something like 4 square root of 3. This is simplest radical form. This is also simplest radical form. The only difference is this one comes out even, this one doesn't. They're both in simplest radical form, but this one I can calculate using my calculator, save myself a step or two. So in these beginning problems where you're doing that, again, no reason to do these intermediate calculations. Those numbers don't matter to the final answer. Let me do one more example again where you'll see simplest radical form and what that looks like. So in this example again, I have a squared plus, or I have a right triangle, so I know that I can use a squared plus b squared is equal to c squared. I identify the hypotenuse as a 6, so I need to make sure that goes to here. So this leg I'm going to use as my a, that's going to be x squared. This leg is also an x, so that's x squared again, equals again 6 squared. Now when you're adding this is going to be 2x squared is equal to 6 squared, which is 36. That's an easy number, so I'll go ahead and multiply that out. I'm going to divide by 2 here, again, to get the x squared by itself. And so I need to take the square root of both sides in order to unsquare that, so x is the square root of 18. Now, simplest radical form means I must look to simplify this radical. So 18, if I do my upside down or my prime factoring, looks like this. I have 2 3's, so those will end up outside as a single 3, and I have one prime factor of 2 left, so simplest radical form is going to be 3 square root of 2, so D would be my final answer. Okay, so again, Pythagorean theorem, a squared plus b squared equals c squared. Most important things, making sure that the longest value, the longest leg, the angle, the side across from the hypotenuse, however you remember it, that must go in as the c value and nowhere else. Otherwise, you're going to have a little bit of a problem. Okay, so we'll look at how we can apply this to other types of problems and the converse in the next portion of this lesson.